Now let me explain to you the meaning of this double integral over the rectangle. So you consider there is rectangle A, B, C, D. Now here let fxy be a bounded function of two variables defined over rectangle ABCD. That means fxy is a function of two variables which is bounded in this rectangle ABCD. That means there exists a lower bound and an upper bound. That means suppose the M denote the lower bound of fxy. That means M is the smallest value obtained by fxy in this rectangle, and capital M be the maximum value or the greatest value of fxy in the in this rectangle ABCD. So now first step, what we need to do now, suppose this rectangle is bounded by the line x is equal to a, that is this line x is equal to b, and then it is bounded below by the line y is equal to c, and above it is bounded by the line y is equal to d. Now let us divide this one. Let a is equal to x naught less than x1 dash dash less than xn is equal to b. That means we divide this line from x is equal to a to x is equal to b into n subintervals. That means x naught will be equal to a, then x1, then x2, we draw a line which passes through the line x2 and so on. And the last one is this one, xn minus 1. And then after that, xn will be equal to this one, will coincide with the line x is equal to b itself. So we divide this interval a to b for x from x0 to xn, which is equal to b. And for c, because y is equal to c for this line also up to y is equal to d, we divide it into smaller subinterval. The first one is this one, it will be y naught, it coincides with this line, y is equal to c. So y naught, y1, y2, yj minus 1, yj dash dash, ym minus 1, ym into m subintervals. So that means c is equal to this one, y naught less than y1 dash dash less than ym minus 1 less than ym is equal to d. Now next step, what we need to do is, through this line x1, you draw a line which is parallel to the y-axis, or x is equal to a. Similarly, through x is equal to 2, x2, we draw a straight line, passes through this point and parallel to x is equal to a, and so on. Similarly, you draw a line y is equal to y1. This one here, this is x0 less than x1 less than x2 and so on. Here it is y is equal to y0, which is less than y1 less than y2 dash dash less than ym minus 1, which is equal less than ym, which is equal to d. So now here we draw a line y equal to y1, y is equal to y2 and so on. Then now next step, let us see this line. The line, this one, you will get a subrectangle, in each of this one. So now let us consider this subrectangle, that means the rectangle which lies inside this bigger rectangle ABCD. It is bounded below by yj minus 1, above it is bounded by the line yj, and on the left it is bounded by the line xi minus 1, and to the right it is bounded by xi. So this one forms another rectangle, but it is a subrectangle of the bigger rectangle ABCD. Now in this subrectangle this one, xi minus 1 to xi, x varies from xi minus 1 to xi, and y varies from yj minus 1 to yj. What we have to do is, now we consider, let mij be the minimum value of fxy in Rij. I have taken that m to be the lower bound of fxy, or m to be the maximum value the minimum value or the smallest value of fxy in this whole rectangle. Now similarly in this subrectangle, this one, we let mij denote the minimum value or the lowest value of fxy in this rectangle Rij. This bigger rectangle is denoted by capital R, and the smaller subrectangle here will be denoted by Rij. That is this one. So now let small mij, this one, small mij, be the smallest value of fxy in that subrectangle, and capital Mij be the upper bound or the maximum value of fxy in this subrectangle. Then after that, we consider the sum S is equal to this one, double summation small mij, aij, where aij represent the area of the rectangle in this region. And capital S is called double summation capital Mij into Aij, where Aij again represent the same area of this subrectangle. Now here in this bigger rectangle, since it is bounded by the line x is equal to a, x is equal to b, y is equal to c, and y is equal to d, the area of this rectangle ABCD is b minus a, that is length into breadth. Length is b minus a, and then the breadth is this one, d minus c. So it is d minus c. So here I've taken Aij to be the area of this subrectangle or smaller subrectangle. Then after that, since that rectangle, or since m is a lower bound, so m into b minus a into c minus a, this will be less than that small s, less than or equal to capital S, less than or equal to capital M into b minus a into c minus or d minus c. Because what we have here is this one, S denote the product of this one, the area into that lower bound, and capital S denote the product of that upper bound in this region into the length and into the area of this region. Now here, since small m is the lower bound and capital M is the maximum or the upper bound or the maximum value, then in that case, that means this will be the maximum value and this is the minimum value. In this subrectangle, even though we have the lower bound and the upper bound, but that one will be greater than this one, and it will be the upper bound will be less than capital M. So therefore, we'll always have this relation that m into b minus a into c minus a is less equal to small s into less or equal to s less equal to capital M into b minus a d minus c. Now in the same way, we can continue to find this one, that say S1 and capital S1. That means S1 represent the double sum of this one, the lower bound, the product of the lower bound of this fxy in this region into the, in this case, xn minus 2, xn minus 1. So it will be the into the area of this region. Capital S1 also will denote the product of the upper bound, that means the maximum value of fxy in this region into the, again, the area of this subrectangle. So we can continue in this way to find so many subrectangle in this bigger rectangle. And if I take this one, the greatest lower bound of the upper sums S, then it is the greatest lower bound of the upper sum S is denoted by I is equal to double integral fxy dx dy, this one, or I, and the least upper bound of the lower sum, because we'll have many capital S and many small s in that subrectangle, because there are so many subrectangles in this original rectangle ABCD. So we'll have many small s and many capital S. Then the greatest lower bound of the upper sum S will be denoted by this double integral fxy dx dy, and the least upper bound will be denoted by this one, I is equal to double integral this bar here, or r fxy dx dy. Now what we have here is that the double integral will exist if these two values are the same. That means if this I1 is equal to I2, that means if the greatest lower bound of the upper sum S is same as the least upper bound of the lower sum S, then in that case the double integral exists, and it is given by this one, double integral fxy dx dy over that rectangle, bounded by x is equal to a, x is equal to b, y is equal to a, y is equal to d. So this is the method of evaluating this one double integral over the rectangle.